tempted by the prospect of looking at dielectrics, so here we go. The main point of the lecture yesterday was that I derived what's called the dipole potential and the dipole field. So we had two charges, plus q and minus q, a distance d apart, and they were oriented. Of course, we can orient our coordinate system as we like, but chose the orientation which is normal, that they're lying along the z-axis. Now, I got asked a very good question at the end of the lecture yesterday, which is, well, you know, you can work out the electric field exactly for a dipole, and indeed, you know, that's elementary first-year electrostatics, and in fact, that's one of the questions I'll be asking for the coursework, is just to review that. But we found that we could get also in the approximation that the distance r here from the centre of the dipole to the point of interest where we're calculating the field, if that's large compared with this distance d, enabling us to make, you know, binomial expansions in small d, we were able to find an analytic formula for the electric potential. Then, of course, if you've got an analytic formula for the potential, you can differentiate it with respect to x, y, and z to give the x, y, and z components of the field. And this was the formula we got. And to emphasize, you have to fix theta, and then once you've fixed the angle, you clearly have got an inverse cube field. QD is, as we described, the dipole moment. 1 over 4 pi epsilon naught is the constant that always comes up in electrostatic problems. So if we take two examples, well, if we go out along the z-axis, clearly theta is 0, cos theta is 1, and we get this formula. If we go out along, for example, the y-axis, and it's certainly a perpendicular axis, well, obviously then theta is 90, cos theta is 0, and we get this formula. It's 1 over r cube field over in each case. So just to give you an idea of what we mean by this approximation, again, remember this dipole approximation only holds when I said r is much greater than d. I was asked, well, you know, how good is the approximation? Well, I just in arbitrary units, I mean, I just let the QD over 4 pi epsilon naught be equal to 1, and then just plotted in the functional dependence, if you like. And you can see, as you go out along either, of course, we can always calculate the exact potential, and then this is from the approximate formula, and you can see that if r is equal to d, the approximation's rubbish. Well, of course, yeah, that's what you'd expect. You know, the binomial expansions that we made wouldn't work. But even when r is equal to about 2d, well, the approximation's out by 10%, but you can see by the time we're out to 10d, so if the distance is 10 times the separation of the two charges, we're actually very, very good with this approximation. We're roughly 0.5% out. So if you want a kind of rule of thumb about, well, when is this approximation going to work, you can say, certainly, if you're just interested in a couple of significant figures, once r is 10d, this is a very good approximation. Now, the important point about the calculation is not that, you know, a pair of point charges often occurs in nature. It doesn't, a pair of exact equal and opposite point charges. But as I got to at the end of the lecture yesterday, any arbitrary distribution of charge can be expressed in terms of a multipole expansion. And if the object has got a net charge, in other words, if this Q, which is the sum of all the Qi within the blob of charge, can of course be non-zero, but for ordinary neutral matter, it's 0. So this first term, the so-called monopole term in the expansion, disappears, but that doesn't mean, emphatically not, that neutral matter has got no electrical effects. It does. It has this so-called dipole potential, and indeed, if we define the dipole moment of the distribution as the sum over I, Qi, di, where these di are the vector displacements from some origin chosen in the middle of the charges, Well, the second term actually becomes identical to what we derive for the dipole potential. So neutral matter, at first somewhat surprisingly, does have an electric field. I mentioned that occasionally in very high symmetry cases this can also disappear, but then there's another term here which goes as R inverse of R cubed, which is called the quadrupole, in a very high, very high symmetry, like a perfect tetrahedron. Even that term disappears, but then there's a next term which goes as R to the fourth, which is a so-called octupole moment of the distribution. And I don't even know if chemists have made a perfectly cubic molecule. They probably have. If they have, even that would disappear, but the hexadecapole moment, which goes as R to the -5, would be non-zero. But for almost everything, it's this term that we focus on. For neutral matter, the lead term is the so-called dipole potential. And one of the things we're going to look more when we come inside dielectrics is water, which has a particularly high dielectric constant. And again, I should emphasize this is very different to the case that I mentioned of carbon dioxide, where you've got a linear molecule, and although there is some displacement of charge towards the oxygens, because it's perfectly linear, the dipole moment does cancel out. The water molecule, the HOH bond angle is about 108 degrees. It's around about a tetrahedral bond angle. You have to do, if you like, molecular quantum mechanics to understand why carbon dioxide is linear and the water molecule is non-linear. That's sort of we'll just take it as a fact at the moment. But this, you might think, oh no, this is going to be something weird. This is going to be a tripole or something. It isn't. This molecule has a dipole, and the dipole is clearly, here we've got a separation of plus minus. The dipole moment of this will be along this axis here. So to emphasize that the dipole potential is a very general property of matter. So again, I put this up at the beginning yesterday to emphasize that when we come, although we're going to get some qualitative, if you like, interpretation of the properties of matter in terms of, we're going to look in the generality of what happens when we apply Gauss's flux law to the problem of putting a dielectric slab in a capacitor. And we're not going to consider conductors or semiconductors at all. That's a massive subject in its own right. You'd have done a kind of simple Drude model of the behavior of electrons in metals. So far, semiconductors reserved for year 3. That's a bit more difficult to understand. You need a good understanding of band theory of solids to do that. But we are going to look just at the insulators. And insulators and dielectrics are the same thing. So that's what we're going to look at today. We're going to look more inside dielectrics, if you like, at all the atomic and molecular mechanisms that underlie the properties of dielectrics tomorrow morning. Today, I'm just going to look at the very general features of what dielectrics do in electric fields. And dielectrics and insulators are the same thing. If you like, in kind of normal English that you'd speak, down the pub, you'd call something an insulator. The physics word for exactly the same thing is a dielectric, but it's the same word. And well, let's just start off with the absolute basics. They're materials that do not conduct electricity. So this is expressed in terms of these absolutely massive resistivities. So you can imagine if you put a 1-volt battery across a piece of quartz or a piece of polystyrene, you get an absolutely negligible current. If you like, the structure of these solids is, again, we can't go into the molecular quantum mechanics of why that's the case. Quartz, if you like, is fully covalently bonded sort of oxygen and silicon structure, where each silicon's tetrahedrally surrounded by 4 oxygens. and the electrons are very, very tightly bound to the silicon and the oxygen atoms and in the bonds between them. So if we put an electric field across it, we can't get any electrons to flow anywhere. So we've just got a material that won't conduct electricity. But that doesn't mean it doesn't do anything in an electric field, far from it. And what does it do? Well, Faraday discovered that. This is something in an electromagnetism course that you can write many times. Faraday discovered that. Well, this is probably yet another of the things he'd have won a Nobel Prize for. Electromagnetic induction was certainly one of them. He discovered the whole field of colloids, my own research field, and he discovered that the capacitance of a parallel plate capacitor, this is the discovery that we're going to follow up, the capacitance of a parallel plate capacitor, that's better, is increased when a dielectric is put between the plates. So, again, this is the kind of thing that Kieran did with you last year in Year 1 electromagnetism. The capacitance of a parallel plate capacitor in a vacuum is epsilon naught A over D. Make that equation 29(2). Again, excuse the, I can't, this was just a sort of general introduction to the subject, and as we're not doing anything on resistance in this course, I'm just going to, this was 29(1) on the VLE notes, so I'm going to leave it out. So, again, in the same spirit as yesterday, I'm making the equation numbers agree with the ones on the VLE. But if you have this is a Greek kappa with a dielectric. So this is the raw fact that we've got to explain, and make that equation 29(3), where kappa, again, I hope this shows up. I'm trying to draw it so it doesn't look like an English K, is the dielectric constant, so-called dielectric constant. And we're going to investigate the origin of the dielectric constant today and tomorrow. This constant, it is also written, and again, this is entirely convertible, there's no difference, as epsilon r, the relative permittivity. This, of course, is the permittivity of free space. This we can write either as kappa or as epsilon or r is the relative permittivity. So, again, just because it's a long, long time ago that you did that, and I'm going to be pursuing materials in parallel plate capacitors for certainly the rest of this lecture, and using the results into the next lecture. Just to remind you, it's a very simple application of Gauss's flux law of electrostatics. Again, we've got that the surface integral of E dot n dA is equal to the charge enclosed by the surface over epsilon naught. This is so easy, we don't even need to bother with the rho dV case. And if you just think of symmetry, if you've got an infinite uniformly charged sheet, well, the surface normal on this side goes that, and the surface normal on that side. Clearly, each of these terms, but again, is symmetrical, that the electric field on either side of the sheet just points out normally to the sheet and is of equal magnitude on the two sides. So integrating over this front face gives me EA, integrating over that back face gives me EA, and the charge inside obviously is the area times the surface charge density sigma over epsilon naught, and the A's cancel, and you get that the E field of a single charge sheet is sigma over 2 epsilon naught. Again, you know, by second year, hopefully you can, you know, work these things through very quickly. And then clearly, if you've got two charge sheets, any Gaussian surface, any Gaussian box that includes both sheets has got no net charge inside it, so it produces zero field. Whereas, or if you like, an alternative way, again, if you think of this as the source and then this as the sink, with all the field lines ending up that way, well, obviously, if you're outside, then the fields cancel, whereas if you're inside, they superpose. And if you've got two lots of sigma over 2 epsilon naught superposing in between the sheets here, we've got E is equal to sigma over epsilon naught. So that's basic Gauss's flux law. The reason we're going to do parallel plate capacitors is the dielectrics are really complicated. So it's nice just to put them in a uniform electric field. And if they're in a uniform field, we get lots of simplifications. So an obvious one straight away is that the electric field, which is in general dV by dx, if this is the x direction between the sheets, is simply just, because it's uniform, is just the voltage divided by the distance between them. Again, we can always rewrite our sigma as Q over A. And then clearly, if we write Q is equal to CV, we can immediately identify this epsilon naught A over D with the vacuum capacitance as written there. So that is the facts. So again, I'll just note this down very briefly. Not going to go through that whole calculation, but for a capacitor, parallel plate capacitor, we've got Q is equal to CV, and V is equal to ED. So if C increases, clearly if C is going up and we've got the same charge on the capacitor plates, the voltage must be lower. C has gone up, this has been held constant, this is the charge on the plates. We now put something in between them and the voltage drops. Well, because the voltage is linearly proportional to the field, the electric field drops. So if C increases for a fixed surface charge, E has decreased. So the dielectric behaves so as to reduce the electric field inside the capacitor. And this, why it does, well, we'll come more to why it does this next time, but we'll do more of the straight mathematical consequences by looking at figure 116. Again, here I've just summarized all the main results that we need, and to emphasize, I can write this as kappa or epsilon r, which is the dielectric constant. So although normally when we have a capacitor we completely fill the region between the plates with, say, a plastic or some other kind of insulator, for the sake of clarity it's been drawn in this diagram with a little gap. So we've got now a situation where remember, this is what we've controlled, if you like. Sigma free, the reason it's given the subscript free is that these charges are free to move around the surface of the conductor. So there's our metal plate. You know, we've just somehow hooked things up. There's our battery, for example. We've just charged the capacitor up. And of course, on the other plate, connected to the positive electrode here, we've got positive charges on the other conductor. Well, we know, just from these very simple considerations, that the overall effect of putting the dielectric in there has been to reduce the field. Well, we know from Gauss's law that if we've reduced the field, we've somehow reduced, if we've got the E dot N dA is equal to Q, the total charge in the box over epsilon naught, and we imagine, again, remember we can put a Gaussian surface wherever we like. Let's put a Gaussian box like this in the system. Well, we know that this hasn't changed. We haven't touched the conductor at all. We've just put a piece of plastic in, and I can emphasize it doesn't even have to touch the conductor at all. Well, we've reduced the electric field, so we must have reduced the charge in the box. So we're forced to conclude that somehow there must be positive charges on the top surface of the dielectric, and again we could have, of course, have done a similar box here, and therefore negative charges on the bottom surface of the dielectric. Can't be otherwise. We've reduced the electric field, so we have to have reduced by Gauss's law, which is an entirely general law, that if we take the surface S to be this box, we clearly have got some kind of reduction. Now, the way, actually, there is displacement of charge everywhere inside the material. I'll make some detailed notes on that, but I'm now just going to look at the dielectric slab itself. So here's the dielectric slab, and the dielectric slab is now pictured in figure 117. Well, throughout, remember, we've got a whacking great capacitor with loads of positive charges here and loads of, I haven't got enough room there. There's that negative charges on the upper plate of the capacitor. And we put this slab in. Well, every single atom is getting what's called polarized by the field. So even if we start out with, for example, a neutral gas atom, something like helium or argon, and of course it's got a spherically symmetric charge distribution. Let's say it's helium and it's got 2 electrons in a 1s orbital. It's completely spherically symmetric electron cloud. But when we put an external electric field across this gas atom, I mean, this is rather exaggerated, but obviously if the electric field goes from positive to negative, the nucleus gets pulled that way and the electron charge cloud gets pulled that way. And although this is a complicated shape now, we know it's going to behave as a dipole. It's net negative, but roughly speaking, the center of gravity of the electron cloud has got pulled towards the positive plate and the nucleus has got pulled towards the negative plate. So the whole thing behaves like a little dipole. So even if it starts out completely spherically symmetric, it becomes a dipole in the electric field. And this is what's called an induced dipole. As soon as we switch the electric field off, the atom just relaxes back to spherical. So it's not that the atom itself has got a dipole, but we've got an induced dipole. We can, as I mentioned, have molecules which have got an inherent dipole moment. And again, we'll come back to this in more detail next time. And now, if we whack an enormous electric field across this thing, of course it's going to tend to line up with the oxygen on this side and the hydrogen. Of course, there are 2 of them, but it acts like a dipole in this direction. These are partially positive charges get attracted to the negative plate and the partial negative charge. So then, if you like, the whole molecule, it's got a permanent dipole. Each molecule's got a permanent dipole moment, but again, in the absence of the field, they're all just tumbling around. All these water molecules are free, they're tumbling, there's no net polarization. But as soon as we switch the field on, it's not that all the molecules line up like soldiers, of course not, and you'll do more statistical mechanics next year. Thermal motion is still shaking them around, but the net orientation is in this sense. So it can be an induced dipole caused by the field, or it can be a permanent dipole which is oriented by the field. In either case, all through the bulk of the material, you get dipoles lining up. Now, the point about the parallel plate capacitor is that the effect only shows up at the surface, because remember there's another layer of dipoles lining up here, and then when you go across plus minus, there will be a cancellation of effects. Likewise, if I keep going here, there's another layer of plus minuses, another layer of plus minuses, another layer of plus minuses, and so on. This polarization takes place throughout the bulk of the material, but inside, only in this very simple geometry of the parallel plate capacitor, where we've got a completely uniform situation, all of the effects cancel out inside, because out of each layer there's some positives, if you like, pushed into it from this direction, negatives from that direction, and it all cancels out until you get to the surface. Now, the surface atoms, there's nothing to cancel out. So it shows up only, although this polarization, this is a polarization vector P that I'm going to define in a minute, exists throughout the bulk of the material, inside everything cancels out and you're just left with a surface polarization charge. And again, it's spread out over the area, so it's usually written as sigma pole. And that's what is illustrated back here in figure 16, is that these sigma pole exist on the surface of the dielectric. And so you see, it's not that sigma pole completely cancels sigma free. It's by no means true. The field doesn't go to zero. It's not cancelled out. It's only reduced. This number isn't infinite. It's a finite number. So that's the idea. And so I'll make some notes now on how that works mathematically. So that's the idea behind what happens, but we've still got a long way to go before we actually calculate the dielectric constant in terms of this polarization vector. And that's the idea of the calculation that's coming up. So this will now all refer to figure 116. So by considering the Gaussian surface S, so we have this Gaussian box here, we conclude that there must be positive charges on the upper surface of the dielectric. And their magnitude is less than sigma free. And again, this is because the material is polarized by the field. So again, this is why this like dipole potential and dipole electric field are so important to us, because if we put any old block, any old slab of neutral matter in between some capacitor plates, it's like we produce this huge number of tiny dipoles inside the material. Their effects all cancel out in between, in the bulk of the material, and only has an effect at the surface. So this polarization, again, sometimes people think that it only happens at the surface because it only has a net effect at the surface. So I'd like to emphasize this polarization takes place throughout the bulk of the dielectric slab. It's like, you know, you can imagine if we put a load of, let's say, liquid argon, make it easy on ourselves, just a nice monatomic liquid. Well, every single argon atom in there gets polarized by the field. But because we've got the argon atoms moving around, there's only a net effect at the surface, but only has a net effect at the surface. And I should emphasise this is only true. I'll come very briefly to inhomogeneous fields and inhomogeneous substances. This applies only to a homogeneous field, in other words, the parallel plate capacitor, and the homogeneous type of substances like a simple liquid. So the electric field induced in the medium is described by the polarization vector P. And this again was illustrated in figure 117 of the course handout. So we've got this idea that we have the polarization taking place everywhere, but there's only no cancellation at the surface. But everywhere inside the material there is a polarization vector P produced by the electric field. Now I want to emphasize this sigma pole that's produced on the surface, it's perfectly real, it's really there, but it only exists while the field's on. It only exists because we put sigma free on the capacitor plates. As soon as we discharge the capacitor and we get rid of sigma free, the sigma pole just relaxes back into the medium. There's nothing left to actually polarize it. So it's real, but only exists because of the external field. So if I now get into the maths on this side, if we assume, let's get rid of this sketch of silica, we assume that in each atom, I'm going to start just with the case of, like a simple atomic liquid. Imagine we've just, the reason I'm choosing a liquid is because we get the averaging of the positions of all the atoms. A lot of what I say when we look, solid dielectrics are incredibly complicated. We'll have a little look at that tomorrow. But today we're just going to assume we've got a simple atomic liquid in between the plates. And if we assume in each atom there are Q charges separated by a displacement vector delta. And I've called that D before. I'm going to emphasize, call it delta to emphasize it's very small. This is of the order of atomic dimensions. This delta, the magnitude will be between 10 to the minus 11 and 10 to the minus 10 of a meter. This is a very small charge separation. Well, then clearly the product Q delta is the dipole moment, and P is given by, well, very straightforward, just linear algebra. P is NQ delta. Let's make this equation 29.6. Is that right? Yes, 29.5 was that last easy equation, where there are n atoms per unit volume. So it's got some awkward units. I'll come to this in a minute. But basically, this gives the electric field per unit volume produced by this polarization effect. So this polarization vector gives you, if you like, the dipole moment per unit volume. Now immediately we can see why we get a huge difference. I'll come to the figures later on between the dielectric constant of a gas and a liquid. I mean, at room temperature, like we're only going to be doing things very, very crudely. At room temperature, a cubic meter of air weighs about a kilogram. and a cubic metre of water weighs about a tonne. You know, very roughly speaking, there's a factor of 1,000 between the density of a liquid and a gas at room temperature at the surface of the Earth. So we're already expecting that if we compare a liquid with a gas, I mean, there are other factors that may come into play, but if we compare a liquid with a gas, we're going to expect that this polarization will be of the order of 3 orders of magnitude, 10 cubed higher for the liquid than the gas, quite simply because there's a lot more atoms to polarize in a unit volume. Absolutely, totally trivial. Again, if we had a cubic metre of lead, it would again be another order of magnitude of atoms to polarize, but we can't worry about lead because it's a metal and it's totally beyond what we can calculate anyway. But roughly speaking, we'd expect gases to have very, very low overall polarization vectors because there are very few atoms per unit volume. Now, of course, that's other factors being equal, and some atoms are easier to polarize than others. If you've got helium, where the electrons are really tightly bound to the nucleus, this is also going to be tiny. And you might expect helium would have the lowest polarization of any substance, and you'd be dead right, it would, because it's got a very low density, this is small, and it's incredibly difficult to separate the charges. If you've got a bigger rare gas atom like argon or krypton, then the outer electrons are more loosely bound, so the pull of the field pulls them, if you like, slightly further apart, and this gets bigger. So there are other factors in there as well, but don't forget this simple n, the number density, is the lead factor. So by dimensional analysis, this is again one of these things that's sometimes skipped over a bit in the first year, but it's incredibly useful. The magnitude of the surface charge density sigma pole, again, given these very explicit subscripts, sigma free because that's the what's on the capacitor plate, sigma pole because it's produced by the polarization, well, it's just given by sigma pole is equal to n delta Q. Again, you can see if there's n dipoles per unit volume and the polarization, you just pull them across through a unit area, you get this very straightforward result immediately, and you can see that this is right. This is dimensionally. This, of course, is in coulombs per square metre. It's a charge density. This is in metres to the -3. It's a pure number density. The delta is a distance in metres, and the charge is moved in coulombs. So if we've got these many dipoles in a volume and we pull them up through a surface, we get this result. And then let's make that 29.7. There's a lot of equations here, but they're basically very, very easy algebra. Just by comparing equations 20, 9, 6 and 7, we get sigma pole is equal to the magnitude of P, which again we usually just abbreviate to P. So that's, you think, well, you know, that it looks very trivial, but we're actually now getting closer to the idea of really solving this figure now. So we're now going to apply Gauss's law to that surface S. We sort of looked at this qualitatively about what should happen. Let's now look qualitatively. So again, this is with, of course, this is with regard to figure 16, applying Gauss's law to the surface S, we get that E is equal to sigma free minus sigma pole over epsilon naught. We could have broken that down into other stages, but again, I think that's absolute. Of course, when the sigma pole doesn't exist. We know that the electric field inside the... previously, of course, we've just called this sigma because we didn't have to worry about anything inside the capacitor. We just had a vacuum in there. But now we've called it sigma free to emphasize it's the charges on the conductor. Well, of course, the electric field produced by the surface polarization charges is also sigma over epsilon naught, but obviously with a negative sign. It's just, we don't even have to think about getting the sign right, because it's very clear that this positive charge is opposite the negatives on this face of the capacitor and negatives opposite the positives on the other face of the capacitor. So, again, trivially, therefore, E is equal to sigma free minus P. We've already proved that sigma pol in terms of magnitude is the same as the magnitude of the polarization vector over epsilon naught. Now, actually there, if you've got anything other than very, very simple geometry, is where the calculation gets stuck. Because dielectrics are incredibly complex materials. So we now... just to emphasize, in general, P can vary from place to place in a dielectric. If I was to put an electric field across a piece of chalk, which has got lots of very complicated constituents in it, many different kinds of atoms, many different kinds of bonds, electrons, nuclei getting pulled in all sorts of complicated directions on the inside, and this P, even in a uniform field, if I've got a non-uniform object, in other words, an object which has got structure, a solid, then I still get stuck, even in the parallel plate capacitor scenario. So, however, this is where we make progress in the maths for a linear, isotropic, homogeneous, in other words, substances that hardly exist. These are the, if you like, our spherical chickens in a vacuum equivalent. It's called an LIH material. We're basically talking now about liquid inert gases. We've got not covering all of materials, to put it mildly, but we can do the maths if we do this. So we have a linear, homogeneous, in other words, it's got a linear response. I'm going to use the fact that the polarization is just linearly proportional to the field. If I put on twice the field strength, I get twice the polarization, which doesn't work for that many materials, although it works quite well at low fields. Isotropic, it's got no favoured direction. It's not like, it's not a kind of layered material like, graphite comes in layers. It wouldn't apply to that because the z-axis is completely different in properties to the x and y axes. And it's homogeneous. In other words, it's the same at every point in space. There are no grain boundaries. So this is a very, very crude approximation for a linear, isotropic, homogeneous material. P is proportional to E at any point. And I should emphasize, this is quite a drastic approximation, and then we're able to then close all the equations and get a nice result. So in this case, we have P is equal, and again, it got defined this way. I can't change this, because this is the way it's done in all the textbooks, and we just have to live with it, where it would be so much nicer if historically it had just got defined P is equal to chi E, and this was, if you like, just a pure number, and this had then would have the same dimensions and therefore units as an electric field. in volts per metre. However, all of this stuff was discovered empirically way before anything was known about atomic mechanisms of polarization, and this is the way the early people defined the polarization vector, and we won't get away from it. If I was to do it in what I think is a conceptually nicer way and make that a pure number, it might make things easier for the lectures, but it would make it different to what you read in every single textbook and every single research paper. So we've got to put it in, and that's the way the definition is, where chi, this is another Greek chi, not a kappa, this is a chi, so I'll just mention Greek chi is used for this symbol, is the electric susceptibility, it's called. Susceptibility, sorry, I've got to get an L in there, ability. I think I've got it right now. Susceptibility of the material. And it's a good word. I mean, it's saying how susceptible the material is to an external field. Given a certain external field, let's say 10, 100 volts per metre, whatever it is we put across the sample, how much polarization do we get for that field? How susceptible is the material? And that, as I say, varies a lot. And particularly, of course, it depends on how tightly the electrons are bonded to the nuclei. So again, I'll just use this board so that we can see the whole calculation at one go. Therefore, E, if we now just want to put these results together, well, we've got already E is equal to sigma free over epsilon naught minus P over epsilon naught. Now, this is just simply rewriting this equation here. We now know that the magnitude of P is chi times epsilon naught times the magnitude of the electric field. So obviously these epsilon naughts cancel. This is maybe why things were done in this way early on. And we take this minus chi E over to this side. So therefore E into 1 plus chi is equal to sigma free over epsilon naught. So again, I'll probably overcook this simple bit of algebra, but E is equal to sigma free over epsilon naught into 1 plus chi. So lots of equations, but very easy algebra. And now we can see, yeah, we've analysed it from this figure 116, and we've got precisely what we want. The field is reduced by a factor 1 plus chi. And if the field is reduced by the factor 1 plus chi, the capacitance is increased by the factor 1 plus chi, and we've defined that factor as kappa. That was the empirical factor called the dielectric constant. Therefore, kappa is 1 plus chi. So we can understand now what Faraday discovered completely empirically, which is that the electric field, therefore the voltage, because it's all linear, inside a parallel plate capacitor gets reduced by this factor, where the chi expresses, and remember this is only for these linear, isotropic, homogeneous materials, the chi expresses how susceptible the material is. Obviously, if this is a very, like for helium, this will be an extremely small constant because there's not many atoms to polarize and they're all got very tightly bound electrons. I'll just finish up. Does anyone need this? Again, a very, very straightforward algebra. Once you've got the idea behind this stuff, the algebra is actually extremely simple. These are now some typical dielectric constants. And so if you've got, and I mentioned helium is probably the lowest known, and remember too, this whole subject is quite empirical. This happens to be at STP, so we're talking about 1 atmosphere's pressure, or 10 to the 5th newtons per square metre. It's just complete accident that that's the pressure at the surface of the Earth. And at 298 Kelvin, which is a complete accident that that's roughly the temperature at the surface of the Earth. And these will all depend on pressure, on temperature, and so on. But you can see that kappa for, and again, I've subtracted 1 from all of these dielectric constants, because in the end, it's the electric susceptibility is the thing we should really be looking at. And you'll see 0.00068. And this is, again, to emphasize that this is a tiny susceptibility. Again, partly, I'm sorry that I changed back to using capital N this year. There's a very low density of atoms, and they've each got a small dipole moment. Oxygen has got, roughly speaking, 1 order of magnitude greater. So we're assuming there's the same number of oxygen molecules, but now the oxygen molecule, the electrons are less tightly bound, so they can be pulled more relative to the nuclei, so the thing is more susceptible. And you can see now we've only got 1, 2, 3, so this is 5. The susceptibility here is 5 times 10 to the minus 4, or if you like, order of magnitude 10 to the minus 3. So for gases, we're going to have very low susceptibilities, and therefore dielectric constants very close to 1, which is why, you know, like when we've got air inside a capacitor, we can say, well, it's more or less like a vacuum-filled capacitor. We've hardly modified the field at all if we've got air at STP in a capacitor. As soon as we go to the liquids, we then go up this 3 orders of magnitude jump. Now, octane, well, that's 8 carbons and, if my organic chemistry is right, 18 hydrogens, all bonded together in a little linear chain. Well, there with octane, it so happens carbon and hydrogen have got almost identical electronegativities, so there's no separation of charge within the molecule, so it almost just behaves like 8 carbon atoms and 18 hydrogen atoms. Each individual atom gets polarized, but the lead effect is that we have this jump just because there's a lot more atoms per unit volume. You'll notice water is completely different. This has got 2 orders of magnitude again higher, but this is because, as I say, we'll come to this more tomorrow, the whole molecule can reorient in the field. This is not like, we're not relying on the fact that the oxygen atom, the hydrogen atom, and the 2 hydrogen atoms, we can slightly separate the electron from the nucleus. The whole molecule, because of the nature of the bonding, is highly polar, so the whole molecule tends to turn in the field, and this gives it, it's called orientation polarization. This gives it a relatively massive dielectric constant, though when it's frozen to ice, it drops back by an order of magnitude, because now the molecules are locked in position in ice, so they can't turn so freely in the field to cancel out the external electric field. So this is a very, very exceptional molecule, and it's rather ironic that the most common liquid on Earth by far, and the one that we reckon might be responsible for life on other planets, is actually a very exceptional molecule. And there's, I think, dimethylformamide, some strange organic molecule, has got a dielectric constant of 100, but of all the common molecules, water has by far the highest dielectric constant. Just to mention, solids are very complicated, because now we cannot just do this averaging. They're very far. Most solids are not linear, not isotropic, and not homogeneous. But just to mention that, again, if you've got a kind of polymer, this is a bit PVC, polyvinyl chloride, it tends to have like a very low dielectric constant, because again, there's not much there that's already polarized, and we'll come to a bit more to the solids tomorrow.